All right, we're good to go.
All right, thanks. Okay. So, I want to walk you through a toy model. So this has, I don't think there's any obvious application right now, so it's not really related to things we would like to observe. It's a toy model that I hope sheds some light on the existence of these differential equations. And I will argue, tells us that there's something more than symmetry behind the scenes. So why are these differential equations appearing so prominently? So this is the question. It's great that they exist. It gives some like holographic flavor to this whole business. They're actually practically very useful. They're easiest way of solving for these correlators. The question is why. So here's a toy model. You take a conformally coupled scalar, meaning you tune the mass. I always forget the number, it's like 1/6 maybe of the Ricci curvature of space-time in phi cube theory for FLRW cosmology, that is power law. So A of eta. If you were de Sitter space, it would be 1 over eta. For reasons that will become clear throughout the talk, I'm going to introduce a parameter epsilon. Okay, so epsilon can be whatever you want. Doesn't need to be small. And I'm going to compute the wave function of the universe at eta equals 0. Depending on the value of epsilon, this is sort of an arbitrary choice because it's not an accelerating cosmology. It's like you're just putting by hand some boundary time slice, and the particle production is just coming from like you imposing some harsh boundary conditions all of a sudden. In some cases, it's natural in an accelerating cosmology. This is really the late time boundary. But for the purposes of understanding what's going on, it doesn't really matter. So we're just going to compute as eta goes to 0. Same story. There will be some decay as eta goes to 0 of the correlator. And then we look at the resulting profile. So it's phi cubed. It's the same scalar everywhere. It doesn't have the richness of what we were discussing the first hour, but it's interesting because now we are in a power law cosmology. It still has some sort of scaling covariance, so it will have some overall power of the exchange momentum, but this is just a distraction, so I'm going to set it to 1. Okay, there's the analog of 1 over s times function of ratio of momenta. I'm going to set it to 1 because it's going to get a bit mathematical. So I'm just trying to simplify notation. Okay? K1, K2. And I'm just focusing on one diagram again. So very simple, very simple. And remember we were talking about these U and V variables. The U and V variables were S over K1 plus K2. An unfortunate, by some unfortunate circumstances, we changed notation. So I'm going to trade this by x1 and It's not very smart. It's just 1 over u and 1 over v, but my brain's hardwired to think about these variables right now for this problem. So if I try to keep consistent with the notation of the previous lecture, I'm going to mess it up. So these are the variables that I'm going to talk about. And I would like to understand this diagram. So now, because everything is conformally coupled, there's some nice technology to handle the time integrals, the explicit time integrals. So the bulk-to-bulk propagator would involve plane waves and so on. And you can do some sort of Fourier transform of the time integrals. So there's some massaging of the time integrals. Leads to... So there are 2 time integrals, eta 1 and eta 2, that you must perform. The mode functions are plane waves, exponentials, okay? But I'm going to do some massaging of the time integrals that I'm not going to explain. It's not difficult. You can ask me later how it works. Some dual variables if you wish. And you will land here. You will land... The 4-point function will be a function of x1 and x2 given by this formula. Yeah, to begin with, the integral doesn't run from minus infinity to 0. It runs from 0 to infinity. And now there are some dual variables. This is roughly speaking time, but not quite. So it's nice because the cosmology only appears sort of in the measure, okay? Notice that the arguments here, modulo the integration variables, go to 0 when the sum of the total energy goes to 0, the sum of the energy flowing in the left vertex goes to 0, sum of the right energy goes to 0. So just the singularities that I was telling you about just a few minutes ago, just the allowed singularities. This one, and the total energy singularity. So if I go back to the Sitter space, I set epsilon to 0, okay? This is sort of a logarithm, one integral. There's some leftover here. I end up with a dilogarithm, Li2, okay? So you can perform the integration explicitly in the Sitter space, okay? And you can even check that it solves the differential equation that I was writing to you just a few minutes ago. If you just set the mass square to be equal to 2 in that case. All right, so this is another nice thing is that the cosmology appears in the measure, so it should remind you of GymReg. Right? In GymReg, we work in 4 plus epsilon dimensions, and then we have p to the epsilon appearing in the loop integration. Okay, so this, I think, is not just some analogy. If you open Georgi's book on weak interactions and you go learn about GymReg on Appendix A or B, he says you should be careful with GymReg because GymReg modifies the infrared of the theory. So you must always look at the infrared of the theory, see if you understand it. Here, the epsilon is also changing the infrared of the theory because it's changing the cosmology, so it's changing the long energy dynamics. And in fact, epsilon will play the exact same role that GymReg parameter plays in other contexts. Okay, so that's my philosophical remark about the appearance of epsilon. So now physics is over, for now at least, and I want to solve this integral. Okay? So what is the value of the integral? So we learned that the right strategy is to find the differential equation satisfied by this integral. So now here's a strategy. It seems like a not a very smart idea, but it turns out to be genius. Okay, it was developed by people working on scattering amplitudes. So first of all, if you look at the integrand, there are 5 critical lines in which the integrand becomes either singular or 0. So 5 critical lines in integration space. So these lines are, let's draw the integration space here. x1 equals 0, x2 equals 0 from the numerator, and then each of these lines going to 0. They carve up the plane as follows. Okay. And then now the idea is consider all integrals of the form f and 1 and 2 and 3 and 4 and 5. This is L1, L2, L3, L4, and L5. So let's consider the space of all such integrals. So now you traded one problem for infinitely many problems, and you don't know how to solve any of them. So it doesn't sound like a good plan. But lo and behold, it's a brilliant idea. So now there are relations. Among the f's, coming from 2 things essentially. One is partial fractions. So if you partial fraction the integrand, you can relate specific choices of the weights to other choices of the weights. Okay? So there are linear relations among the, just one example, 1 over x1, x1 plus let's see. It's easier to take residues. Sorry, I'm slow. Just one second. Okay, so this must be equal. Okay. Maybe this is the smart way to do it. Okay, so I hope this is correct, but you know, it's partial fractioning. It's nothing deep. So if you put this inside of the integrand, it implies, for example, that f and 1 plus 1 and 2 and 3 plus 1 and 4 and 5 times x1 plus 1 equals f and 1 So you see, it allows you to lower the weights. So you have some high overall weight, and you can lower it by 1 unit by using this relation. So it means that if it's a generic member of the space, then you can relate to members of lower weights. And not only that, you can integrate by parts. Okay, so integral of any total derivative is 0, therefore you also generate other relations among the members of the basis. And when I integrate by parts, the epsilon is crucial. It's necessary to set the boundary terms to 0. So I'm going to work with a range of epsilons for which I can throw away all boundary terms and then hope that I land on my feet at the end of the day, okay? Just like you work in GMREG, you assume that it's the vanilla case, everything is simple, and then you send the epsilon to your desired value at the end. So, from these two things, a remarkable fact follows that, to be honest, I don't know how to prove, but it's true, and it's known by mathematicians. Because you can integrate by parts and there's some total derivative operator, there's some cohomology business in this running in the background. Now, because there's some cohomology and these are rational functions, modulo these weights here, the connection is not just the exterior derivative. It's like dressed by that factor of x1 and x2 to the epsilon. So people call this twisted cohomology. Okay? So there's some cohomology business running in the background, meaning that it looks like you could have all sorts of integrands, but there are only a few that are truly independent from each other. So then it's a theorem that I don't know how to prove, related to twisted cohomology. You can forget these words later if you want. The basis is finite dimensional, but here's the amazing result. And the size of the basis, number of bounded regions. Go back to this figure, count bounded regions. 1, 2, 3, 4. So it's 4-dimensional in our case. So it means that you don't need to solve for infinitely many integrals. All you need to do is solve for 4 of them. If you solve for 4 of them, then you're done. But, wow. Okay, I traded 1 problem for 4 problems. But now, because it's a vector space, any operation that I do on the members of the basis must be writable in terms of the basis. In particular, so let's build a basis. Let's call it psi. We put our original integral here, f, and then we have to pick f2, f3, f4. We'll talk about what you should pick in a second, but naively you just take 3 other values of these n's, assuming that they are not that there's no relation, that they're not trivially related via integration by parts or okay? Just 1 second. Now, any operation that I do on this psi must be writable in terms of psi itself. In particular, I can take the differential. Take the differential of psi. Psi, of course, depends on kinematics, right? Psi is a function of the external kinematics. Now take a differential. Well, I change these guys, but it's just some differential, so it's just changing the powers that appear here. I just argue to you that it's within the vector space, therefore You must be related. Okay, so this is your differential equation. So now anything you can dream of about this system is encoded in this matrix A. Any differential equation follows from linear algebra. If I pick 5 vectors in a 4-dimensional vector space, there must be a linear relation among them. So now take, for example, f, derivative with respect to x1 of f, all the way to 1, 2, yeah. So these are 5 vectors, and they must be linearly dependent. So how do you find the differential equation? Well, the first derivative of f is a function of the members of the basis. The second derivative of f is, is it clear? You just rewrite each one of these guys as a linear combination of these 4 members of the basis. Now you have 5 free coefficients and 4 functions in the basis, so there must be a way of setting everything to 0. So then you find that they satisfy a linear relation. Okay? So the fact that the basis is 4-dimensional automatically tells you that you should find ordinary differential equations of at the very most 4th order. You can find partial differential equations as long as you collect 5 such members in the basis. Yes, question? Is that clear? So in this framework, the differential equations are a consequence of linear algebra. Okay, so any differential equation you wish follows from linear algebra. They're all homogeneous. Remember that the differential equation that we wrote a few minutes ago was inhomogeneous, but that's not a problem. Take delta u plus m squared f equals uv over u plus v. Well, let's do something simple. 1 u plus v over uv. Take du. And this is on the nose what this machine will give you. Okay? This machine will generate this equation for you. So you need to work a little bit harder to see that it reduces to the inhomogeneous system. But it's possible.
It looks like you get 4th order equation.
Yeah! Oh, I didn't tell you the matrix A. This is math. Physics hasn't come back in. Yeah, this is applicable to any integral. Any integral. In fact, I could have changed. I put epsilon L1 and L2, but I could have put different epsilons on each of the lines, and the same story would apply. I would have a 4x4 matrix that would depend on all the 4. So this is a math story, and then I'll tell you physically there's some property of the matrix A that is related to physics that will give much simpler things than you would naively expect. Okay? So this is the generic expectation, but the physical example, it turns out to be simpler than this.
Why aren't we starting with just 3 lines from the start? Why are we including L1 and L2?
Because that's where the integrand becomes singular, right? There's a cut there, and it's necessary to kill off the boundary terms.
No, I just thought that you still have that in the numerator. So x1, x2.
Yeah, but when I write integration by parts identities, I will naturally, because this is epsilon, I'll naturally have epsilon and x1 downstairs. So it will appear naturally. Yeah. It is necessary to, well, if you remove those 2 lines, there would be a single function, right?
Yeah.
One bounded region. But then you can't integrate by parts, so the counting is different.
Or it gets created.
Yeah. Yeah. All right. Now I must tell you. Well, so this was a shock to me. But you know, the surprises are not over. Now here's another observation. That the function that comes from physics It's not just any integral of the family. It's a very special two form. It's kind of a unique two form associated to one of the bounded regions. So this is the two form. You see, it's singular on the triangle L3, L4, L5. But it's essentially the unique form that has logarithmic singularities at all of the edges. Okay, so it's not just singular. It has logarithmic singularities because it's dx over simple power of each of these. So this is called the canonical form. Of this bounded region. So let me tell you a couple of things about this canonical form. So maybe 4.1. So like a little mathematical digression. So the canonical forms are the forms that have logarithmic singularities at some prescribed boundaries, and they're essentially unique up to normalization. So log singular at prescribed boundaries, unique up to normalization. So here's an example, 1D. Very simple example. Take 2 points, minus A, minus B. Let's find the canonical form associated to this interval. So the canonical form must have logarithmic singularities at both points. But the relative sign is also fixed because I can't, otherwise I'll have a pole at infinity. Okay? So in order to cancel the pole at infinity, I must subtract so that when I send x to be very large, I get the x over x minus the x over x. Okay? So modulo the number that goes up front, I'm gonna choose to set the number, the absolute value to be 1. So modulo flipping, this is unique. Okay? Now for a triangle, so this works in any number of dimensions. So for a triangle, the canonical form slightly different. So for a triangle, let's do simple triangle. Two of the lines are the axes, and then this is ax1 plus bx2 plus c. Then the canonical form is going to be like c okay. So the C here is just the determinants of this C here is the determinants of the coefficients of each of the, it's like 1, 0, 0. So that's what this C is doing. So if you want to do 3 generic lines on the plane, you would put the 3 lines downstairs, and you would take the coefficients of each of the lines to normalize the canonical form. Now, okay, this looks very trivial, so can I carry on? If I take 4 lines, can I just write 1 over L1, L2, L3, L4? That doesn't work. why do you think it doesn't work? It has too many singularities. Look. It's singular here, right? When I send these two lines to 0, it's not just singular at the edges. So I want it to be singular only within this domain. But if I just put this here, it's telling me it should be singular at this edge also, this point. Okay. Likewise, it's telling me it should be singular. Okay, let me make a bumpy line here. It should be singular at these other points. So what's the cure? So you must add the numerator that's made out of this line here. Okay? So it's not entirely trivial how to find these canonical forms beyond the simplest possible geometric regions. The good news is that it's triangulation independent. So a simple-minded way of going about this, if you don't want to draw these pictures, you can triangulate. So instead of, so this is one possibility. Another possibility is you triangulate. You introduce, say, a line here. You compute the canonical form for this triangle, canonical form for this triangle, and you adjust the sign, the relative sign, in such a way that the singularity along this line here cancels. Okay? Then the claim is that the canonical form is unique. It doesn't matter if you choose another triangulation. Okay? So these canonical forms are special because they have, for our context, they're special because they have the following property. So they have all sorts of magical properties, but for us, one that will be nice is that if I take a differential of a canonical form with respect to external data, okay? Let me call it external data, meaning I take a differential not with respect to x1, x2, I take differential with respect to a, b, c, okay? Because when I do these integrals, the true data of the results will be the data of the lines, right? The inclinations of the lines and so on. So if I take a differential with respect to the external data, it's a total derivative. It's a total derivative in the integration stuff, x1, x2, etc., of something. Okay, let me call it omega. So therefore, it means you can integrate by parts. If I literally integrated just the canonical form, this would just give me a boundary term. Okay? But remember, there is this epsilon here. So when I take the differential, when I hit the canonical form, I would get a total derivative. Then I can integrate by parts. Or I hit the twisted part. So what does that mean? It means from this, it implies that A, if we choose the basis psi to be integral x1, x2 to the epsilon. So our first entry, the physical correlator, is the canonical form associated to one of the bounded regions. This one here, region 1. But then what should we do? Take the canonical forms of the other regions. You can choose whatever basis you want, but it's this basis is making life much simpler. Yes?
This seems very reminiscent of the stuff that shows up in S matrix calculations as well.
This is the method. But it's in some sense even cleaner because there you need to work hard to find the right basis. Well, here, in this integral representation, it's already like giving you explicitly what the basis should be. You just find the canonical forms. There you need to work a bit harder to find the right basis.
Presumably this is related to this cosmological polytopes.
Yeah, so the integral form that I showed for the 4-point function comes from the cosmological polytope. But these other integrals here, they don't appear there because the polytope is developed in flat space or in de Sitter. So these other regions are kind of like, I don't know, twisted cosmological polytopes. I don't know. They're other things.
Does also something special happen? I can't remember this, where this omega goes to 0. Is that also a special region?
Ah, you mean if I shrink one of these things to 0 size? Yeah, so then you need to analyze carefully. There are like certain blow-up conditions that you need to check how fast it goes to 0. Then you might need to modify the basis in that case. But here, for the cases that come from physics that we are interested in, this doesn't happen. This phenomenon doesn't happen. Okay, so if we choose this basis, then something nice happens. A is epsilon times something that is epsilon independent. So the only appearance of epsilon is here up front. Okay? In that basis. Otherwise, epsilon appears all over the place. And this is nice. Well, in amplitudes, it's a dream come true because you want to work as epsilon goes to 0. So then you get a very accurate prediction by solving. So you have to solve d plus epsilon a psi equals 0. So the solution is given by the Dyson series, right? So some path order exponential integral epsilon a acting on some initial state vector. So this, you compute the integrals at some specific kinematics. They will have epsilon dependence, and then you can send epsilon to 0. So you just keep a couple of terms in the Dyson series. Well, that's very nice. Okay. Moreover, it implies a couple of other things. The fact that it's proportional to epsilon means that now, maybe I shouldn't. Implies, if I take D again and use the equations again, implies that it's abelian flat, actually. And the commutators are all 0. Maybe, well, just to be clear, this is like index-free notation. The matrix, this is the differential. Is differential with respect to each kinematical variable, right? I'm always afraid of this very sleek notation. So this has the components in the kinematical direction x1 and x2. Therefore, A has components in the direction x1 and x2, and they commute the matrices. Okay. Not only that, A is abelian flat, and lo and behold, A is given by the following. It's a 4x4 matrix. Almost. Okay. So these are 4x4 matrices, where all the entries in each of these matrices are either 0, 1, and -1. Okay? So it looks like binary, the matrix. Okay? So it's like 0, 1, -1, and it encodes the dynamics of the diagram. So it's automatically abelian flats, right? Because if I take D, it's like D squared everywhere. Okay. And it has the singularities in all the right places. It has E total singularity, E left, E right. It has these folded singularities that the physical solution shouldn't have. That's it. So it has the singularities in all the right places. And it has these zeros, ones, and -1s that look randomly distributed. And that's where physics comes in. The physical diagram is such that the distribution of the zeros, ones, and -1s is special in a way that I don't understand. Okay, and I'll show it to you how special it is. Well, first of all, I understand technically why, but I don't understand why it's so simple. Why is it like 2, 3, 4/3, like a -1/2? It's just 0. It's somehow avatar of the fact that we pick these canonical forms with unit residues. Okay, but I don't fully understand physically if it has some meaning, some geometrical, like, I don't know, linking number between the various bounded regions. And it would be nice to be able to write down from the get-go, this is the ansatz for the matrix A, and just have a geometric picture for all the entries. I don't know how to do that. But, okay, so from this a lot of things follow. Something cool also is that, well, if I change epsilon to epsilon plus or minus integer, I can just forget about that and just change some numbers here, right? So it means, in particular, it means that the cosmological correlator computed in A of eta equals 1 over eta, eta to the epsilon, must be related epsilon plus or minus integer. So if I change the value of epsilon by some integer, in particular, send epsilon to 0. So when eta goes to 1, this is flat space. A of eta is a constant. So there is a relation between the wave function computed in flat space and the wave function computed in de Sitter. Just because if I change things by an integer, I'm still in the same vector space, so there must be a linear relation among the different wave function coefficients. So it implies, by the way, all interesting cosmologies in this parametrization are integer values of epsilon. Matter domination, radiation domination, things like epsilon equals 2 and 3, and so on. Okay? So it implies some relations between the computation of the wave function in different cosmologies, and it just falls on your lap in this. It's automatic. There's like you don't need to work hard for it. Now, as I said, because the basis is 4-dimensional, you would expect a 4th order equation. But the matrix not just gives you a method to find the differential equations, it also tells you how to, in some sense, efficiently solve it. If you change basis, you could have said, well, let me just diagonalize the matrix, and then that's it. I just diagonalize the matrix and go home. But if you change basis, psi equals then A doesn't quite change by a similarity transformation. It changes like a gauge field. So A tilde will be N. So it looks like you're not making much progress. You found eigenvalues, you diagonalize the first term, but then you induce another non-diagonal matrix from this differential. Well, unless the eigenvector is kinematics independent. If it doesn't depend on kinematics, this term is 0, right? So for all eigenvectors that are kinematics independent, it looks like you can make some progress. For this example, there are 4 eigenvectors, and 3 of them are kinematics independent. And this is a physics thing. For a generic integral, all the eigenvectors, in fact, give you an example. If you take this and just do the following, epsilon 2, epsilon 1, okay, or even epsilon over 2. Okay, just change tiny bit. Then all eigenvectors are dependent on kinematics. So there's clearly something, some input that's coming from physics here that gives 3 eigenvectors that are independent on kinematics. And then when you change bases, A tilde will be the following form. A, B, C. Well, as you would expect, so it diagonalizes part of the matrix, but then the 4th column is left untouched. Okay, so you have I don't know, D1, D2. Okay, so now the original function is some linear combination, because I changed bases, some linear combination of these 4 new members. But okay, but now it should be obvious to you how to solve the equation. Right? I solve for the bottom entry, and then it just appears as a source in like linear differential equations in each of the remaining functions. And then just add them up, and I'm done. Yeah, so you can write, for this particular example, you can write the full answer. It's some sum of hypergeometric functions. But it's not obvious at all from the integral. From the flat connection and this change of basis, then it's kind of given to you. Okay? So you're like, okay, well, maybe this is not so exciting because it turns out that the differential equation is 3rd order. Remember, the inhomogeneous equation is 2nd order. I hit it with an extra derivative. I get a 3rd order equation. Well, the basis method predicted 4th order. So there's some extra structure. You lose 1 derivative. Who cares? Okay. You can work out this example. This example has 3 integrals. So now the integration space is 3D. And there are 9 critical planes. So you start carving up. 6 of them form a cube. So like 2, 2, 2, 1 bounded region. Like, great. Then you just cut it 3 more times. Okay. You end up, how many bounded regions do you end up with? Just out of curiosity. 5, 10, how many? 11, 12, 1 million. You end up with 25 bounded regions. Okay? So it means that you get a matrix A that is 25 by 25. That will capture, and you would predict that the differential equation is of order 25. It turns out that, well, it's not hard to guess. Each propagator, you need the 2nd order differential operator to collapse it. So 2 derivatives, 4 derivatives, you get a context term, you kill it with an extra derivative, 5th order. So even though it's 25 by 25, there's so much structure here that it collapses to a 5th order equation. Okay, so clearly this is like a crazy hammer to kill a little fly, right? In this example, it works just right, but here it's way overkill. There's a lot of inputs that is coming from the physical integral versus the generic twisted integral, is related to locality of the space-time diagram, and I don't know what's going on. So, and, yeah, I worked this out, and I'm trying to find the basis and blah blah blah. Yeah, it turns out that you can again reduce the whole thing to a 4x4 block, 4x4 block plus 21 inhomogeneous equations. So there's just a ton of structure here. It's some input that's coming from physics. And it's just a nice way of organizing the computation, and it gives you insight of where the differential equations come from. It gives you all these relations between different cosmologies and so on. Okay, so just to wrap up, I hope in these lectures I showed you a bit of our current efforts to try to understand where these initial conditions come from. There is a fighting chance that human beings will be able to see this in the sky, like measure scattering amplitudes of primordial fluctuations in the sky. It requires a lot of theoretical work in many directions, from computing them, predicting the signals, to actually connecting them to the data, to making the signals large enough to be detectable, to understanding the mathematical structure of how to do these computations, understanding the consequences. For example, I didn't have a chance, but there are many consequences of locality and unitarity for the structure of the correlators, cutting rules, bounds on certain coefficients, and so on. So it's really exploratory right now. Everything that I talked about here was 3 level. We don't understand the analytic structure beyond 3 level. We don't even understand how to do efficiently computations with external spinning particles. We have some results. So there's just a lot of stuff to be explored. Okay, and I feel that there are many directions in the sense of trying to decode the hologram for the de Sitter space, making connections to like more formal areas of black hole physics and so on, all the way to connecting to data and observations. So with that, I'm done. Thanks a lot.